Hello, my name is Katie Perkins, and this is my Lab 4 Circuits and Capacitors for Physics 2212. The purpose of this lab was to predict the behavior of circuits, ohmic resistors, and capacitors in a variety of settings. The goals were to answer all of the lab questions, draw all of the lab graphs, and to calculate the RC. My RC from the graph was 5.99. The relevant physics concepts included the node rule, which says the current in must equal the current out, and the loop rule, which says the potential difference of a round trip is equal to 0. Ohm's law, which says V equals IR, the conservation of energy and charge, the fact that voltmeters have an ideally infinite resistance, ammeters have an ideally zero resistance, and this lab-specific equation. The experimental model included two parts. Part 1 was the charge conservation and energy conservation in a series circuit, where Part 2 looked at a RC circuit with the charge and discharge times, as well as the time-dependent voltage across a discharging capacitor. The experimental setup for Part 1 included two 1.5 volt batteries, two resistors of 47 ohms and 100 ohms, and two ammeters. First, I was told to predict the ammeter readings before the circuit was connected. I predicted that it would be equal to 0.02 based on the total voltage of 3 volts and the total resistance of 147 ohms. When I connected the circuit, this prediction was accurate. When the ammeter was reversed, the reading stayed the same, so this concludes that we don't have to worry about the direction of the ammeter for the remainder of the lab. After this, I replaced one of the ammeters with a voltmeter. The voltmeter read 3 volts and the ammeter read 0 volts, as the voltmeter has ideally infinite resistance. After I removed it and reconnected the circuit, I saw that the voltage across both the batteries was 3 volts. The potential difference across the 47 ohm resistor was negative 0.96 volts, and the potential difference across the 100 ohm resistor was negative 2.04 volts. The sum of all of these was equal to 0, as corresponds with the loop rule. Next, I drew a graph of potential versus position around the circuit using my voltmeter readings from the previous part. When attaching the voltmeter, the ammeter reading doesn't change because the voltmeter ideally has infinite resistance, so the current does not travel through. This is why, when connected across a 100 ohm resistor, the current is still 0.02 amps. Next, I replaced the voltmeter with an ammeter in parallel to the 100 ohm resistor. This increased the current readings to 0.06 amps. This is because the ammeter ideally has zero resistance, so the current travels through that instead of the 100 ohm resistor. This means that the current essentially has 47 ohms of total resistance now. Based on my potential difference measurements as well as my ammeter readings, I calculated the resistance of each element. Like predicted, the first resistor had a resistance of 47 ohms, while the second resistor had a resistance of 100 ohms. The wire is 0 and the ammeter additionally 0 ohms. For the next part of the experiment, I needed a 10 ohm bulb, a 20 ohm bulb, one 9 volt battery, a 200 millifarad capacitor, and one bulb is connected at a time, as seen to the left. After I connected the 10 ohm bulb in series to the capacitor and the battery, the light quickly turned on and then faded away. Then I disconnected the battery and connected the capacitor to the 10 ohm bulb. Once again, the light turned on and then faded away. I then recorded the charge and discharge times for the 10 ohm bulb and additionally the 20 ohm bulb. In this chart, these are average values of triplicate measurements of these charge and discharge times. Next, I set up a circuit with a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm bulb. I measured the voltage across the capacitor with the voltmeter as it was discharging. I plotted this data for 20 seconds. Due to the previously mentioned formula and the linearization of this formula, when I plotted the change in voltage over the initial voltage versus the time, the slope should be equal to the negative 1 over RC constant. Since my slope was equal to negative 0.167, the RC from the graph was equal to 5.99. From the simulator, this would be equal to the resistance times the capacitor, so that would equal 6. These values are extremely close. Some sources of error included that we were using an online simulator, so the voltmeter and ammeter did not have their ideal resistance. In addition, it was difficult to start the timer exactly as the circuit was connected, so all my values are probably off by a certain amount, which may account for the y-intercept. If we were doing this experiment with a real ammeter, it would be different because a real ammeter does not have a zero resistance. The inclusion of an actual ammeter would increase the resistance in the circuit and result in a lower overall current. In addition, if we were charging a capacitor with no resistor in the circuit, a battery would be able to charge a capacitor instantaneously. However, in reality, wires do have internal resistance, so this could not happen.